Hello everyone. Today we will discuss a topic from the subject Industrial Engineering. Okay. So the name of the topic is network flow models. Okay. So generally this topic is little bit different from the network flow models or network models which we see at the beginning, right? So in the sense there are so many network models. Okay. So first network models which we see in the industrial engineering subject are PERT and CPM, right? So these are network models, the PERT and CPM. Okay. So these network models are used in the project management, right? So there are some more network models, okay, which we call it as network flow models. Okay. So these network flow models are having a different application when compared to the network models which are PERT and CPM. Okay. So today in this session we will discuss the network flow models. Okay. So generally there are two types of network flow models which we have in our GATE examination syllabus. Okay. So the first network flow model is minimum spanning tree algorithm. Okay. And the second one is the shortest route algorithm. Okay. So generally questions has been asked in the GATE examination from these algorithms also. Okay. So these algorithms are a little bit different when compared to the PERT and CPM. Okay. So in the application point of view, so these PERT and CPM are applied in project management, right? So what we do in PERT and CPM, we find the project completion time, right? If it is CPM, we find the project completion time, right? So if it is PERT networks, we find the expected project completion time, right? So these models, network flow models, okay, are having a different application. Okay. So we'll discuss one by one. So PERT and CPM are for project management. These are a different. Okay. So when we come into the topic, we'll discuss one by one, right? So our topic is okay. So these two models are there in our syllabus. Okay. First one is minimal spanning tree algorithm and shortest route algorithm. Okay. So please don't confuse these models with PERT and CPM. Okay. So this is my first request, right? So these models are having different application and different procedure also. Okay. So first we'll start with minimal spanning tree algorithm. Okay. We will see what is the practical application of this. Okay. Maybe in industries or maybe in our other sectors. Okay. And then we'll go to shortest route algorithm. Okay. So the first algorithm is minimal spanning tree algorithm. Okay. So first we'll try to see what is meant by tree. Okay. And then what is meant by spanning tree, right? And then what is meant by minimal spanning tree. Okay. So there is a GATE question asked in the exam year 2014. Okay. So it was a theoretical type of question. So after discussing this theory part, okay, we'll go and we'll see what is that question also. Okay. So as far as the examination is considered, so mostly theoretical type of questions may be asked from this. Okay. Because if they go for a problem, it will be a little bit lengthy. Okay. So it may not be asked for 2 marks or 1 mark. Okay. Because lengthy problems will be there in this particular algorithm. Right. Okay. So I'm just taking a network. Okay. Similarly, you might have seen so many network diagrams in PERT and CPM. Right. So I'm taking a network diagram here. So a very small network diagram, right? So now the basic difference between the network diagram in this particular spanning tree algorithm and the network diagram which we see in PERT and CPM is there is no directions in this particular network diagram, right? So whenever we see the network diagrams in PERT and CPM, we see some arrow marks, right? So there will be an arrow mark from 1 to 2, 2 to 3, like that, right? So the specialty of this algorithm is this algorithm can deal with the network diagrams which are not having any directions. Okay. So the network diagrams which we see in PERT and CPM are directional network diagrams, right? And these network diagrams are non-directional network diagrams. Okay. So it is a project management. It is different application. Now we will see what is the application of these particular network diagrams, right? And then we will come to the procedure. Okay. Now we will take an example. Okay. Say for example, there are 4 cities. Okay. So there are 4 cities. So I'll give a question like this. Okay. So now with the help of the question, we will try to understand this algorithm, or with the help of an example, we will try to understand this particular algorithm. Okay. So there are 4 cities. So 4 cities are there. Okay. So connect these 4 cities. Okay. So now we are having 4 cities, maybe 1, 2, 3 and 4. Right. So there are 4 cities. Now our task is to connect these 4 cities with minimum length of the road. Okay. So if length of the road is minimum, then the expenditure which we spend or the cost which we spend for building this road will be minimum, right? So say for example, government is building road among these 4 cities. Okay. So it wants to know what will be the minimum length of the road to connect all these 4 cities, right? So this is our basic problem. Okay. So we take this example and we will try to understand this particular algorithm, right? So there are 4 cities. We have to connect these 4 cities with minimum length of the road. Say we assume that lengths will be 15, some 20, 25, 30, like 12, and maybe again it is say 50. Okay. So these are the lengths of the road. Say for example, from city 1 to city 2, if you want to connect, so length of the road will be say for example 15 kilometers. Okay. So from 2 to 3 it will be 20 kilometers and so on. Okay. So these are the kilometers, these are the distances in kilometers. Okay. Now this we call it as, let's try to look at some terminology. Okay. So these things which we have written here, we call it as weights. Okay. So we call them as weights, right? So these weights may be, now we have taken in terms of distance or in terms of length, right? So these weights may be in terms of time or maybe in terms of cost also. Okay. So here we have taken distance, but it may be a distance, or it may be time, or it may be cost also. Okay. It depends on the particular problem. Now we are dealing with the distance. Okay. So it is a distance in our case, but it may vary. Okay. So it may be time or it may be cost or anything. Okay. So this we call it as weights. Now this we call it as nodes. So it is similar terminology when compared to CPM and PERT. Okay. So these we call it as nodes or vertices. Okay. So these we call it as arcs or edges. Okay. So this is just a terminology. So similar thing we will be seeing in CPM and PERT. So we call this as arc. Okay. So now we use 2 types of terms here, which is arc or an edge. Okay. So this is just a terminology, right? So now our aim is to connect these things with minimum length of the road, to connect all these cities with minimum length of the road. Okay. So this is a general example. Okay. So when industries are considered, right? So these algorithms are used in industries also. Okay. So whenever there is a situation, say for example, there is one machine here, one machine here, like so many machines are there. Okay. So whatever the components or raw materials has to move from one machine to other machine, right? So then what will be the minimum length required? Okay. So that we can find using this algorithm. So this is general example. Okay. So this is having applications in industries also. Say your lot of raw material is moving from one machine to other machine. Okay. Says there are so many machines. Okay. So what will be the minimum distance which these raw materials can move? That we can find using this type of algorithms. Okay. So our first thing is, now we will see what is a tree. Okay. So now we have seen what is the practical application of this algorithm. Okay. So this is general application which we have taken here. So we are having some applications in industries also. Okay. So I have taken a small network here. Okay. So it might be looking very small. Okay. So it is a small network which we have taken here. Okay. But there might be so many big networks also. Maybe having some 10 nodes, 15 nodes. Okay. Like that. Right. So first we will see what is a tree. So I am just taking a subset of this network. Okay. So this is a network. So from this network I am taking a subset. Okay. So say for example this is 1, 2, 4. Okay. So this is the example for a tree. Okay. So this is not a tree and this is a tree. Okay, so if you observe the difference between these two diagrams, okay, so this diagram is having a closed loop. Okay, so if this network is having a closed loop, we cannot call this as a tree. Okay, so if this network is having an open loop, okay, we can call this network as a tree. Okay, so first of all, this is a non-directional network because it is based on the applications. Okay, so there is no restriction that you can build road only from 1 to 2. You can build road from 4 to 2 also. Okay, so in this direction also you can build. Okay, so that is why there is no directions for this particular network. It depends on the application part. Okay, now this is not a tree because it is having a loop. Okay, so when there is a loop, we cannot call this as a tree. Okay, so this is not having loop, no loop. Okay, so this is a tree, right? So a tree should be a subset of the given network with no loop, right? So this is the definition of a tree. A tree is a subset of a given network diagram or given network with no loop. So we can draw so many number of trees here, right? So we have seen only one tree right here. So we can draw from this, we can draw so many trees like 1 to 2, 2 to 4. Okay, so this is also a tree. Okay, so like this, so many trees we can extract from this particular network. Okay, so this is the basic definition of a tree. Now understood, right? Okay, so now we'll try to understand what is a spanning tree. Okay, so first part we understood what is a tree. Okay, and the next part is we will see what is a spanning tree. Okay, so before that we will try to generalize some things here. Okay, so here there are nodes or vertices. So I am just writing nodes. So there are 3 nodes. Okay, and the number of arcs is equal to 2, right? So there are 3 nodes and the number of arcs are 2. Okay, so we'll try to generalize this thing. So when there are n nodes, your number of arcs will be n minus 1. Okay, so this is a condition for tree. So when you are taking a network diagram, okay, when you are taking a subset of a network diagram, given network diagram, okay, so if that subset contains n nodes and n minus 1 arcs, then we can call that as a tree. Okay, so this is the example, or this is the general notation for a tree or definition of a tree also. Okay, so now we will try to see what is a spanning tree. So a spanning tree is also a tree with some special case. Okay, now this is a spanning tree. Okay, this is also a tree because it is not having any closed loop, right? So this is a subset, right? Subset of this network. It is not having any closed loop, right? So this we can call it as a tree. Okay, now it is a spanning tree. We call this as a spanning tree because if we look at this network diagram, okay, so there are 4 nodes or 4 vertices. Okay, if you look at the network diagram and if you look at this subset, in this subset also we are having 4 nodes. Okay, when all the nodes of a given network are present in a tree, we call that tree as a spanning tree. Okay, so when all the nodes of a given network are present in a tree, we call that tree as a spanning tree. Okay, so this tree is a spanning tree because it is having all the nodes of the given network. Okay, we can call this particular tree as a spanning tree. So when any of the node is missing, we can just call that as a tree. Okay, which we have seen previously, right? So this is a spanning tree. Whatever the things which you have seen previously. So in that examples, I have taken only 3 nodes. That's why I was just calling that as a tree. Now it is a spanning tree because it contains all the nodes. Okay, so like this we can extract so many spanning trees from this. Okay, so we can extract so many spanning trees from this given network. Okay, so I'll just take some more examples. So okay, so this is also a spanning tree. So 1, 2, 3, it is 4. Okay. Okay, so this is also a spanning tree because it is having all the nodes and open loop, right? So we can take some more examples like 1, 2, so this is 4 and this is 3. Okay, so like this we can extract so many spanning trees from this particular given network. Okay, so now we will go a little bit forward. So I am just writing the weights or kilometers distance. Okay, so 15, 20 and this is again 15. So this is 15, 20, this is 12. Okay, so this is 15, this is 30 and this is 15. Okay, now I am just calculating the total distance or total weight values for this particular spanning trees. Okay, so total weight, I am just writing it as total WT is equal to 15 plus 20 plus 15. Okay, so 30 plus 20 it is 50. Now here total weight is equal to, so this is 15 plus 12, 27, so it is 47. Okay, so 15 plus 15 it is 30, so again it is 30, so total weight is equal to 60. Okay, so like this you can draw so many spanning trees and you can calculate the total weight of all the spanning trees. Okay, now whichever the spanning tree among these having minimum total weight, we call that spanning tree as minimal spanning tree. Okay, as simple as it is. Okay, so many spanning trees will be there. So whichever the spanning tree having minimum total weight, we call that spanning tree as a minimal spanning tree. Okay, now you might be thinking that it is a very laborious process, right? Because there might be some 10, 15 spanning trees. We have to draw all the spanning trees and we have to find the total weight of all the spanning trees, right? So you might be having a question, right? So this is just theoretical part for explaining what is a spanning tree. Okay, so there are other algorithms also using which we can directly find the minimal spanning tree. Now we have written here only spanning trees, right? So there are some algorithms under this. Okay, so which using them we can directly find a minimal spanning tree from this particular network. Okay, so that we are not discussing now in this session. Okay, so first we have seen what is a tree, right? And then we have seen what is a spanning tree and then what is a minimal spanning tree. Okay, so now in this case our total weight is distance, okay, in terms of kilometers. Okay, now the application, or if you look at this spanning trees, so if you connect a road network like this, okay, so you have to lay a road of 50 kilometers. Okay, so if you connect like this, you have to lay a road of 47 kilometers. Okay, so if you connect like this, you have to lay a road of 60 kilometers. Okay, so it is the meaning of that, right? So this is the concept of the minimal spanning tree algorithm. Okay, so tree, spanning tree and minimal spanning tree. Okay, so now we will see a previous gate question based on this particular topic. Okay, so it was a theoretical type of question. So he was just asking the definition of these things, minimal spanning tree. Okay, so we'll try to look at that particular question. Okay, so this question has been asked in the GATE examination 2014. Okay, so it is based on the minimal spanning tree algorithm. Okay, so the question goes like this. Have a look at the question. The minimal spanning tree in the network flow models involves option A, all the nodes with cycle or loop allowed. Option B, all the nodes with cycle or loop not allowed. Option C, shortest path between start and end nodes. And option D, all the nodes with directed arcs. Okay, so this is just a theoretical type of question. So what could be the answer? So answer will be option B. Okay, so it is the definition of the minimal spanning tree, right? So all the nodes with cycle or loop not allowed. Okay, so we have seen when it is a tree or a spanning tree, all the nodes with cycle or loop is not allowed. Okay, it is the basic definition of the tree. Okay, right. So we have seen the first algorithm, which is minimal spanning tree algorithm. Okay, so we have seen the application part of it. Now the second algorithm is shortest route algorithm. So second algorithm shortest route algorithm. Okay, so again this particular algorithm is having a different application when compared to PERT and CPM, and when you compare this with the minimal spanning tree algorithm. Okay, so please do not confuse this algorithm with PERT and CPM algorithms. Okay, so I will tell you where the confusion comes while solving the question, or while we will take an example and we will try to solve that example with this particular algorithm. Okay, so again there is a previous gate question on this particular algorithm. Okay, so after discussing this algorithm, we will try to solve that particular question, right? Okay, so let's take an example problem to understand this particular algorithm, shortest route algorithm. Okay, so this algorithm is also known as Dijkstra's algorithm. Okay, so with this particular example, we will try to see what is the shortest path. Okay, so now again we will try to see what is the application part of this. Okay, so we have seen what is the application part of the minimal spanning tree algorithm, right? So we will see how it is different from the minimal spanning tree algorithm. Okay, so if you observe again, the basic difference here is this is a directed network, right? So this network is somewhat similar to the PERT and CPM network, right? So somewhat I cannot say it is similar to the PERT and CPM network, right? So if you can see, so there is no difference between this network and any network which we deal in PERT and CPM, right? So this is a directed network. So the non-directional networks which we have dealt in minimal spanning tree algorithm. Okay, so the basic difference between that algorithm and this algorithm is, first thing is the application part, and the next thing is, so it is not having any, it is having directions. Okay, so this is a directional network. Okay, so this you have to remember. So your minimal spanning tree algorithm is a non-directional networks which we have dealt in that particular algorithm. Okay, so let's try to understand what is the application part of this in our day-to-day life or in real life. Okay, say for example there is a person, okay, who is here. Okay, now this person has to travel from city 1. Okay, say for example there are 7 cities. Okay, so this person has to travel from city 1 to city 7, say for example. Okay, now what could be the shortest path for him to travel from city 1 to city 7? Okay, so this is our problem now. Okay, so the name itself indicates it is the shortest route algorithm, right? Now what we have to find? We have to find the shortest route for this particular fellow who is at city 1. Okay, he has to reach city 7. Okay, now what could be the shortest route for this fellow who is standing here at the city 1? So he wants to travel to city 7. Okay, so this is our problem. So find shortest route from city 1 to 7. Okay, so again there is no difference in the terminology. Okay, so this we call it as nodes and this we call it as arcs. Okay, so everything will be similar, right? So there is no difference in the terminology. So this we call it as nodes and arcs. Okay, so now we have to find the shortest distance from node 1 to node 7. Okay, so there are 7 cities. So this fellow has to reach from city 1, has to travel from city 1 to city 7. Okay, so now the important thing is this particular fellow who is standing at city 1, okay, need not travel all the other cities, right? Because so there is no need. Okay, the aim of him is to travel from city 1 to city 7. Okay, so he need not there is no need to touch all the cities. Okay, so previously we have seen the minimal spanning tree algorithm, right? So in that, so whatever we have taken at the final stage, okay, whatever the network diagram we have taken at the final stage, okay, so there we have seen that spanning tree should be having all the nodes of the given network, right? So that is the difference again. Okay, so this fellow has no need to touch all the cities. Okay, so he can travel from city 1 to city 2, 2 to 5 and 5 to 7, like that. Okay, or else he can travel from this path or else he can travel from this path. Okay, so now we have to find which path is the shortest path for him from this to this, right? So this is our problem now. Okay, so we can take one more example like this. Say so there is no direct train. Say for example he is traveling with a train. Okay, so he is traveling by a train. Okay, so there is no direct train available from city 1 to city 7. Okay, so if you want to take a train, he can take train from 1 to 2 or 1 to 3. Okay, so direct train from 1 to 7 is not available, so you can take from 1 to 2 or 1 to 3. Again after reaching 2, so you can take only to 5 or maybe from to 4. Okay, so it is like that. So if your problem is like this. Okay, now say for example this, again these are weights. Okay, so again these things are weights. Say for example this is a time taken. Okay, so time taken will be 15 hours. Okay, so in our case the weight is time. Okay, so just we are assuming that for traveling from 1 to 2, this fellow is taking 15 hours, or this particular train is taking 15 hours of time. Okay, from 2 to 5 it is 25 hours, and so on, right? Now this is our problem. So this is the real life application part, right? So he has to travel from city 1 to city 7. Okay, so now we will see how this algorithm works. Okay, so this algorithm we call it as Dijkstra's algorithm, right? So we will see how this algorithm works now. So it is little bit similar to the CPM and PERT, where we calculate earliest start times and latest start times, right? So it is little bit similar. Please do not confuse with that. Okay, so I'm just taking boxes like this. I'm just taking cells like this at each and every node. Okay, now I'm just assuming that this fellow is starting at time t equal to 0. Okay, so you started at time t equal to 0. Now if you want to move to city 2, it will take 15 hours. Okay, from here to here it is taking 15 hours. Okay, so little bit similar procedure when you compare with the calculation of earliest start times and latest start times. Okay, so from 1 to 3, so it is taking 20 hours of time. Okay, so now from 2 to 4, this will be 15 plus 10, it will be 25. Okay, or else 20 plus 15, it will be 35, right? So now between these two we have to take 25. Okay, so now this is the major difference between the PERT CPM problem and this algorithm. Okay, so there we were taking 35. Okay, so it is a project management and it is having some different application. Okay, so there we were taking 35, but here we have to take 25. Okay, so this is shortest route algorithm. Okay, shortest route. Okay, so shortest value we have to take. Okay, so this is the basic difference. Please do not confuse with those PERT and CPM algorithms. Okay, so similarly for others also. So 15 plus 25 it is 40. Okay, so 20 plus 20, so this will be 40. Again 25 plus 15, this is also 40. Okay, so this will be 40, so there is a tie. Okay, so both are minimum. Now this one 40 plus 10, it will be 50. 40 plus 20, it is 60. 25 plus 30, it is 55. Okay, so the minimum among these three will be 50. Okay, so this is how the algorithm works. Okay, so similar procedure, but the only difference is you have to take the minimum value because it is a shortest route algorithm. Okay, so now the shortest route from city 1 to city 7 is 50. Okay, so shortest route from 1 to 7 is 60 hours. Sorry, it is 50 hours. Okay, so now you might be getting some doubts like how we calculate, how we take these paths in CPM and PERT. We just take the paths like this and we calculate the total values, right? So then also we can get the same answer, but the beauty of this algorithm is not only from 1 to 7, okay, so from city 1 to all other cities, we found the shortest paths. Okay, so if you take like that, if you take the paths like this and if you calculate, you can calculate the shortest path only from 1 to 7. Okay, so the beauty of this algorithm is from city 1 to all other cities, we found the shortest paths. Okay, now the shortest path from 1 to 5 will be 40. Okay, so shortest path from 1 to 5 is 40 hours. Okay, so shortest path from 1 to 6 will be, so 1 to 6 is also 40 hours. Okay, so like this and so on, you can calculate the shortest path from city 1 to any other city. Okay, so that is why we have done this much procedure here. Okay, so in the examination there is no guarantee that he is going to ask to find the shortest path from 1 to 7. Okay, so he may be asking to find the shortest path from 1 to 5, maybe from 1 to 4, or maybe from 1 to 6 and any other path. Okay, so that is why you have to follow this particular algorithm. Okay, so if you know this particular algorithm, you can find the shortest path from any node to any destination node. Okay, so or from any city or from the first city to any other city. Okay, so this is the shortest route algorithm, right? So this is just a general example, okay, which I have taken to make you understand how this algorithm works. Okay, so there is one GATE previous year question, so which is based on this particular algorithm. Okay, but these weights are not given directly. Okay, we will try to look at that particular question. Okay, okay, so the given question is GATE 2008 question, so it is based on the shortest route algorithm. Okay, so the question goes like this: for the network below, the objective is to find the length of the shortest path from node P to node G, right? Let Dij be the length of the directed arc from node I to node J, full stop. Let Sj be the length of the shortest path from P to node J. Which of the following equations can be used to find Sg? So a diagram, network diagram has been given, right? So option A, Sg is equal to minimum of Sq comma Sr. Option B, Sg is equal to minimum of Sq minus dqj minus, comma, Sr minus drg. Option C, Sg is equal to minimum of Sq plus dqg, comma, Sr plus drg. Option D, Sg is equal to minimum of dqg, comma, drg. Okay. So there is network diagram given, right? So this is based on the shortest route algorithm. Okay, so they have directly not given the values. Okay, so they have directly mentioned that there are some shortest paths. Okay, so first we will try to see what is the given data. Okay, so I'm just drawing the network diagram which they have given. Right, so this is the given data. So they have given a network diagram. Okay, so just we have, in place of nodes, they just have given dots. Okay, so please don't confuse with this, right? So they have given a network diagram and they are saying that Dij, okay, so these are Dij values, right? So previously we have seen the weights. Okay, so it may be a distance, it may be a cost, or it may be a time. Okay, so these are Dij values. Okay, these are Dij values. Okay, so Sj they have given. Sj is the length of the shortest path, okay, from node I to node J. Okay, so the meaning of this is the length of the shortest path from P to Q will be Sq, right? So previously what we have done, so we have calculated, we have taken boxes and we have calculated the shortest path. Okay, so from city 1 to any other city we can find the shortest path, right? Now what they are saying is they have directly given, so they have directly given this box and this box. Okay, so Sj is the length of the shortest path. So SQ will be the length of the shortest path. Okay. So if you go with the values, so you will get SQ value in this particular box, right? Which we have already seen in the previous example problem, right? Now this will be SR. Okay. So now SQ will be the shortest path from P to Q. Okay. Or from city 1 to city, or from city P to city Q. Okay. So which we have seen in the previous example, right? So SR will be the shortest path from P to R. Okay. So now what they are asking? They are asking us to find the shortest path from P to G. Okay. That means what they are asking? They are asking us to find the shortest path from P to G. That means SG is equal to question mark. Right. So this we have to find. Now what will be this? So they have given Dij. So Dij is the weight value. Okay. So this will be DQG. Okay. From node I to node J. Okay. So your node I is Q, your node J is G. Okay. So similarly for this, so this will be DRG. Okay. So now what we have done? We have to add this. So what we should be writing here? What should we write here? So this will be minimum of SQ plus DQG, comma SR plus DRG. Okay. So whichever the value minimum among these two, that we are going to write in this particular box. Okay. Which we have written already in the previous example. Right. It was a numerical example. There we have seen. Okay. Now what is your SG? So your SG, that is the shortest path from node P to node G. Okay. Is equal to minimum of SQ plus DQG, comma SR plus DRG. Okay. So this particular thing is your option C. Okay. So now option C is the correct option. Right. So option C is our correct option. Thank you.